Well, welcome back, folks, and let us get into our new unit, and that is our unit on gases. So, let's start with this. Consider any gas you want. Oxygen, nitrogen, argon, all those gases have some things in common. Here's the question. What are the basic assumptions we hold about the particles of these gases? Okay, let's consider some notes then. Let's start off with gases. Okay, and let's try to put down a framework, kind of a broad definition. I'm not going to give you a simple definition, but kind of a broad definition and a set of assumptions that we use when we think about gases. The first thing is we know that gases are, or a gas is a state of matter, correct? Just like a solid liquid, we also have a state of gas. And in this state, in which, what do we know? Do we know any characteristics of state of matter in which the matter has no definite shape and no definite volume? Okay, so that's not a bad definition, right? We say, hey, gases are things that have no definite shapes and no definite volumes. So it's a state of matter in which, this is kind of silly written, isn't it? In which matter has, okay, in which it's a state of matter in which there is no definite shape and no definite, in which there are, let's get our English right, in which there are no definite shape and no definite volume. Good. Is that sufficient? Yeah, for the time being. Now, we want to add some more stuff here. I'm going to put a line right here, and we want to talk about something called the kinetic theory, because this will help us better understand gases. It goes beyond a definition, and really it's a set of assumptions. Good. So what is the kinetic theory? Well, the kinetic theory is, let's go with our definition of kinetic theory. It is a theory which describes or predicts the behavior of gases based on what? Well, what does kinetic mean? Kinetic means motion, yes, based on the motion of gas particles. Okay, cool. So now we know what the kinetic theory is, but what are the key assumptions? All right, this is the stuff we really need to know. What are the key assumptions about my kinetic theory? Okay, where are we going with this? We're trying to understand gases. One part of understanding gases is the kinetic theory, and what are the key assumptions about the kinetic theory? There are 5 we want to know. Number 1, gases are composed of a large number of tiny particles far away from each other relative to their size. Yikes. Man, am I going to have to memorize 5 assumptions like this? Yeah, you probably are. Gases, let's get my English right though. Gases are composed of a large number. That means billions and billions. Well, I don't know billions, but millions, a whole bunch, more than I can count. Number of tiny particles probably are billions and billions. Tiny particles, it's a large number, but each particle is small. It's not, it's composed of large particles. No, it's composed of a large number of tiny particles. And these particles are far away from each other relative to their size. In one sense, what we're saying here is that you have a large number of particles, but each of the particle volumes is negligible. Okay, negligible meaning we don't have to worry about the particle volumes. Number 2, gas particles are in continuous. What does continuous mean? Always moving. Continuous, random. Hey, I don't know where they're going. Rapid, really fast. Gas particles are in continuous, rapid, random motion. Okay, cool. That one's not so bad. Motion. So, okay, number one is that the gases are composed of a large number of tiny particles far away from each other. Number two, that these particles are moving very rapidly. They're moving all the time, and they're going in all kinds of directions. Number three, there are no forces of attraction between gas particles. Well, forces of attraction, what am I talking about here? Well, you guys know some forces of attraction, right? How about London? How about dipole-dipole? How about hydrogen bonding? That's right. All of these IM forces do not exist, we're assuming, between the gas particles. So when two gas particles go by each other, there's no effect of them being close to each other, okay? And number four, that is, if my two gas particles don't indeed go by each other, but crash into each other, what happens? And the answer there is that the collisions between gas particles are elastic. Yikes. Like a rubber band? What do you mean elastic? Well, elastic is a physics term, and what we're saying is that elastic means there is no net loss of total kinetic energy. Okay, that means essentially, hey, if usually when a collision occurs, what happens when a car hits another car? Well, you'll hear a big bang. That means some of that kinetic energy is transferred from kinetic energy to the energy of sound. Or there might be some heat that is generated. So some of that kinetic energy is transferred to heat. In this case, we're saying there is no transfer, no loss of the motion, of the energy of motion in these collisions. Okay? Now, do you really need to comprehend this? No. For our purposes, you just need to be able to spit this back at me. And number five, the temperature of a gas really reflects the average kinetic, yipes, why can I not spell kinetic? Average kinetic energy of the gas particles. All right, but now we need some more. What is average kinetic energy equal to? Well, my average kinetic energy is equal to 1/2 mv squared, where m is the mass of my gas particles, or my gas particle, and v would be what? The velocity of the gas particle. Okay, let's analyze this for a minute. We're saying that average kinetic energy is a function of mass and velocity. Well, if I assume my gas particle has the constant mass, what does that mean? So let's assume that my mass is constant. If my mass is constant, if my kinetic energy goes up, what must have happened? Well, that meant that my velocity of my particles must have gone up. So my velocity of particles go up. That means my kinetic energy goes up. If my kinetic energy goes up, that's a measure of what? Temperature. My temperature goes up. Oh, so what you're telling me, Mr. Smith, is that when I have a gas at a higher temp, what does that mean? Well, that really means that those gas particles are doing what? Well, that those gas particles are moving faster. It means those gas particles have a increased or a higher velocity, right? Oh, cool. Yeah, isn't that neat? The temperature reflects essentially the motion of the particles. Now, what happens if my velocity goes to 0? What if my particles are not moving? Now, not just the velocity, but hey, I mean, my particles could go like this. They can move in that direction. They can move in that direction. They can move in that direction. Hey, this particle could also go back and forth. It could go up and down. It could expand. The bond can expand. It can compress. And all of those are forms of movement. What happens if all this movement stops? No movement. Well, if there's no movement, then my velocity is 0, and if my velocity is 0, then my average kinetic energy is 0, and if my average kinetic energy is 0, then what do I have? I have a temperature of 0. And what do we call this temperature of 0 when everything stops? We call that absolute 0. And the scale that's based on absolute 0 is your Kelvin. So that means that 0 Kelvin is equal to absolute 0, meaning my particles no longer, the gas velocity, they're probably not gases at this time, the velocity is equal to 0. Yikes! You get all of that out of the kinetic theory? Yes, I do. One other thing, and then we'll be done. Gases which obey the kinetic theory, gases which for which these assumptions hold true, we call ideal gases. So an ideal gas is a gas which obeys, I would say, maybe that's a weird word, obeys the kinetic theory, obeys the assumptions of the kinetic theory. And what are those again? Number one, an ideal gas does what? It is composed of large number of tiny particles far away from each other. An ideal gas is in continuous, rapid, random motion. An ideal gas has no forces of attraction. An ideal gas has what? A collision that is elastic, and when I look at the temperature of the ideal gas, it reflects to me what? Its average kinetic energy, and it reflects to me its volume. Woo, mama. And that's all for this one question. Yes. So your answer here would be those 5 points, those 5 assumptions of the kinetic theory. Let's call it let's call it a day here. Next time we'll talk about a little bit of pressure. Okay, see ya.